What's here on the screen will actually be two different videos, one with systems of linear inequalities, and the other will do a little review of polynomials and exponents as we move into the last part of the unit. So systems of linear inequalities. You've done linear inequalities in previous courses at some point. So these are the ones where you shade half the plane because something is either less than or greater than something. So you're not looking for intersections that are single points. You're looking for regions where anything in that region works as a solution to the inequality. Little reminder, when you graph these things, if it's greater than or less than, use a dashed line so it doesn't include that boundary. If there's that little underscore, like greater than or equal to, then you're going to use a solid line to indicate that we're including that line as one of the boundaries. So a couple of quick reminders, graph the inequality. Y is less than x. So start by graphing what looks like y equals x. Y equals x would be a line that goes through the origin, right? So it goes through 0, 0, and it's got a slope of 1. So up 1 to the right 1, up 1 to the right 1, or down 1, left 1. The next question is solid line or dashed line. When I look at this and I see that there's no little, it's not like a less than or equal to, that would be include the line. But this one is not. It simply says less than. So we're going to make a dashed line. You're going to do it with a nice ruler. I'm going to do it with a tablet as best I can. Okay, that's my dashed line. Now I have to decide which side to shade. Well, I can pick any point that I want. So let's say I pick the point 0, 2. Where's 0, 2? Right here. I got to pick a point, by the way, that's not on the line, because if I pick a point on the line, it's not going to help. So pick a point that's not on the line. 0, 2 is not on the line. So it says that y is 2 and x is 0. Is that true? No, it's not true. 2 is not less than 0. So if that's not true, then you shade the other side. So I shade down here. Anything I pick down here will work as a solution to that inequality that says that y is less than x. So I'll pick a random point. This one right here. What is it? 1, 2, 3, 4, 5 over and 2 down. So x is 5, y is negative 2. Y is negative 2. X is 5. Boom. Works. Anything that I pick in that shaded region will work. Anything I pick that's either on the boundary or not in the shaded region will not work. All right, let's try that third one down there. I'm going to need the space. I'm going to erase what's over here and graph that third one. The third one is already set up in y equals mx plus b form, so I can graph it pretty easily. Y-intercept is negative 3, so I come down 1, 2, 3. There's my y-intercept. Slope is negative 1, so I can either go down 1 to the right 1, can do that a couple times, or I can go up 1 to the left 1. Either way. This says less than or equal to, so I can include that boundary in my line. Now I got to test the point. I'm going to test the point 0, 0. Nice, easy one to test. So if I'm going to test 0, 0, put a 0 in for y, put a 0 in for x. Is 0 less than negative 3? No, right? Because that negative 3 is negative. 0 is not negative. So the negative 1 will always be smaller. So don't include 0, 0. So 0, 0 is up there. I'm going to include everything that's not 0, 0. The other thing you can do is you can look at the way the equation is written. It says I want all the y values that are less than that line. So where is less than is underneath. So underneath negative x minus 3 are all the things that point below. All right, what if I gave you this second one over here? Said let's graph that. If I want to solve this, divide both sides by negative 2. Remember, there's a rule that says when I do that, if I divide by a negative, the sign flips. So instead of being less than 8, it's now going to be greater than. And then 8 divided by negative 2 is negative 4. So how do I graph that? That's not one that has both an x and a y-intercept. It's a vertical line. So here's negative 4 on the x's. Dashed line because it says greater than, so we don't include the line itself. Greater than negative 4 is anything over here. All right, so I'm going to shade to the right. I'll put the arrows at the end of my line, and there it is. So if negative 2x is less than 8, then it's another way of saying x is more than negative 4. There's my solution. Right? The same thing for the y is less than 2 one underneath it. Instead of being a vertical line, that's going to be a horizontal line. So y less than 2 would be a line that extends this way across here. And then less than is underneath, so down the bottom. Right? Anything down there is less than 2. All right, well, so those were individual ones. How about systems of linear inequalities? Well, when you graph the two lines in the previous section, systems of equalities, you were graphing the two lines to see where they intersect each other. Well, you're going to do the same thing here, except instead of the intersection being an individual point, your intersection is going to be a whole section of the coordinate plane. So you're going to look to see where the shading overlaps. Right. So again, a reminder about solids and dashed lines. And if you want the location of the intersection point, then just assume that there were equal signs and solve the system that way to get the intersection point. And then you can figure out from there which way to shade and see how they overlap. So let's start with a very simple one, and then we'll move into other ones. If you got colored pencils at home, this might be a good time to get like a yellow and a blue, because yellow and blue make green, and you'll see where they overlap. What other colors do that? Red and blue make purple. Or you can grab a standard number 2 pencil and shade one way and one the other way and see where the overlaps and the crisscrosses are. All right, so y is greater than -2. How do I graph y is greater than -2? Well, y equals -2 is a horizontal line. This says greater than or equal to, so I'll include the negative. So I'll include the boundary. Here I am at -2. Which way do I shade this? I shade up. Right? Y is greater than -2. All right. How about the other one? The other one is x is less than -3. So I know that's a vertical line. It says to include the points in the boundary, so I'll include the points in the boundary. Less than -3 means I'm shading to the left, right? Those are all the places where it's less than -3. So do you see that there's 4 quadrants, for lack of a better term here? The one on the top right only satisfies the blue equation. The one on the bottom left only satisfies the red equation. The one on the bottom right satisfies neither of them, but look at the top left. The one on the top left satisfies them both. So my solution is this part here. It comes across here, it goes down that way, and it includes everything in there. So everything in that region satisfies both equations. If I want the intersection point here, it's -3, -2. All right, so this is a very simple case of a horizontal line, a vertical line. Where do they overlap? That's where they overlap. I might suggest shading them lightly at first, and then once you find the intersection point, darken the shading so that I can see what the final answer is. All right, let's take a look at this one. This one is a set of 2 oblique lines. They both have equality, so they include the boundaries, right? Neither of them are dashed lines, they're both solid lines. So take a look at the first one. Y is less than or equal to x plus 4. I know the y-intercept is 4, the slope is 1. So the y-intercept is 4, 1, 2, 3, 4, and the slope is 1. So up 1 to the right 1, up 1 to the right 1. I can do that a few times. I can go down 1, left 1. It's the same thing. And I make a line. Now, some people like to graph both the lines first and then they shade. Some people like to shade first so they don't forget. If I'm going to shade less than or equal to x plus 4, I'm going to shade down, right? I could try putting a 0 in for x and a 0 in for y. And 0 is less than 4, that's true. So I put a 0, 0 in to get that. If it's true, then shade the side that includes that 0, 0. If you put a 0, 0 in and you don't get something that's true, shade the other side. All right, take a look at the next one then. The next one is -2x minus 3. So y-intercept of -3 and a slope of -2. So I can either go down 2 to the right 1, down 2 to the right 1, or I can go up 2 to the left 1. Like that. Right, which way am I going to shade this one? It doesn't go through 0, 0, so I can test that. Put a 0 in for y. Put a 0 in for x. And yes, 0 is more than -3, so I'm going to shade this way. Right, you can see where they overlap. If you want the point of intersection between them, at least the way it's graphed on my little grid, it doesn't look like a nice, simple point of intersection. So to find the point of intersection, set the two equations equal to each other since they're both already solved for y, and see what you get. So find out when x plus 4 is equal to -2x minus 3. All right, so add a 2x to both sides. And I get 3x. Now let me also, here I'm going to sneak a subtraction in there. Subtract a 4 from both sides. X equals -7/3. Okay, no way I would have figured that out just from looking at my graph, although it's kind of accurate, right? -7/3 is -2 1/3. So -1, -2, look, is -2 1/3. Okay, I'll take it. And then if you want the y value, put that back into the first equation. So y would be -7/3 plus 4. So 4 is the same thing as 12/3. 12 minus 7 is 5. Right, so 5/3 is 1 2/3, and sure enough, my y value is more than 1, but less than 2. So if you were asked to find the intersection point, that's the intersection point. -7/3 for the x, 5/3 for the y. The actual solution is that whole sort of triangular region on the right that has the crisscrosses between the two different colors. All right, one more and then we'll look at an application problem as to how we can use something like this. So I've got two equations that look kind of similar to each other. Right? Maybe I'll solve both of these for y and see if that helps me to graph them. Or the other option I have is I could put in some values for x and y and see what I get. All right, so on that first one, call this the red one. If I subtract a 3x from both sides, I get -y is less than -3x plus 2. Divide through by -1, but don't forget when you do that, it switches the sign. So you get +y is greater than +3x minus 2. Right? So when I divide through by -1, it switches the inequality sign. It also changes the signs of all the variables and numbers. So 3x minus 2 has a y-intercept of -2 and a slope of 3. So it's pretty steep. Up 3 to the right 1, up 3 to the right 1. I could even go down 3, left 1. Right, it's a dashed line, not a solid line. And if I put a 0 in for x and a 0 in for y, I get 0 is greater than -2, which is true. So I'm going to shade this one that way, because it just makes that 0, 0. All right, let's pick a different color and solve for the other one. Down here, I get -y is greater than -3x minus 2, right? Subtract that 3x from both sides. Divide through by -1 and switch your signs. Y is less than 3x plus 2. So here's my 2. Slope of 3 says go up 3 to the right 1, up 3 to the right 1. Hopefully you notice I'm making parallel lines here because they both have the same slope. Okay, dash lines as best we can here. You can grab a ruler and do this. Put a 0, 0 in here. Notice it goes just above the 0, 0. And I get 0 is less than 2. So 0 is less than 2 is true, so I'm going to shade this thing that way. So the overlap in this case is a very narrow band that goes between those two lines, right? Can you see that the actual overlap is this little region in the middle here. That's where the two colors intersect. By the way, if it were flipped around, like if the two signs were flipped, the red one went to the right and the blue one went to the left, you would end up with a no solution because there would be no solution, no intersection between those two shadings. You would end up with sort of a empty gully in the middle between those two lines, and one went to the right, one went to the left, no intersection. So there's no solution if that were the case. So it is possible, even for these types of problems, to have no solution. All right, let's take a look at one more where it's an application problem that's already been graphed for us, and we just want some information. So a kennel owner wants to fence a rectangular pen for dogs. The length has to be at least 50 feet. The distance around it should be no more than 140 feet. What are the possible dimensions of the kennel? So we're restricting, maybe we only have 140 feet of fencing. So the distance around it should be no more than 140. But yet, I want the length of the kennel to be at least 50 feet. I want the dogs to be able to run back and forth at least 50 feet. So I've got length and I've got width. Now, what did it tell me? It told me that the length has to be at least 50. So if the y is the length of the kennel, then the length has to be at least 50. And the distance around it should be no more than 140. So distance around it, we're thinking of a rectangle here, right? So rectangles have congruent sides top and bottom, congruent sides left and right. So if I add up x plus y plus x plus y, the distance around it is 2x plus 2y. So that's how we get those equations. The length has to be at least 50. The distance around it has to be no more than 140. So it can be 140. That's why it's less than or equal to. So no more than means it can be 140, but no more. Graph the equations, that's what you get. Y equals 50 is that red line. 2x plus 2y equals 140 is that blue line. So I'm shading above the red line, but below the blue line. Any combination of length and width in this region here that's bounded by the axis and the two lines will work. So for example, let's pick a point that looks like it's in between. Okay, so maybe I pick this point over here. It looks like that point over there is x equals 10 and y equals 55. So it meets the first criteria that the length of the kennel is at least 50. And if I add the distance around, 55 plus 10 plus 55 plus 10 is 130. So yes, it meets both criteria. Could I have picked this point in here, let's say 5, 60? Sure, 560 will work. 0.65 will work, although that's kind of a silly solution because it's not even wide enough for the dog. So maybe like 265 will work, something like that. So all the different combinations that are inside that shaded region will work for this kennel that meets my two criteria. I only have 140 feet of fence, so I can't make it any more than that. And the length has to be at least 50 because the dogs need a little exercise and they can run around. And that satisfies both of them. All right, it's the end of this section. End of this chapter, really.